someone asked a question on this, how the pressure will be different and all that. Is he present today? Someone was asking last class about Bernoulli and something.
Yes, sir.
Okay, fine. So let us go ahead. So we talked about flow in a pipe, and then we said that there is a pressure difference between 1 and 2. Fine. So first the question should be that is there a pressure difference at all, and why is there? Or what are the factors that are playing here? Now the challenge what I face here is that you need some concepts of fluid mechanics. Okay, this is not strictly speaking part of thermodynamics, and fluid is another subject I think you will be having in this semester or next semester. This semester you have fluid mechanics. Can anyone please tell?
No, sir.
Okay, so most of this you need some advanced concept. It will be like seventh or eighth chapter, but I will try to explain in a simple way. So let us see what is going on here. So basically, when you have a fluid flow in a pipe, okay, so you'll have a velocity profile which is parabolic in nature, and near the wall, okay, when you have fluid flowing past a wall in a wall bonded type of flow, there will be some shear force, okay, in both the sides. So basically what happens is if you take the full circumference of the tube and you integrate, you see that there is a net force on fluid, okay, due to wall shear. That force is in this reverse direction, opposite direction to flow. So that net force is in this direction. So now we know that fluid is moving at constant velocity, right? So we see that one force is acting here. Now to balance that, we should also have some force in the forward direction, right? Newton's first law. Because the fluid is not accelerated, it is going at constant velocity. So the net force should be zero. So we know that one force is acting in the reverse direction. So one force should also be there to balance it. That's all. Is this okay with everyone?
Yes, sir.
Yes, sir.
Fine. So that force is coming from the pressure difference. Okay, we provide some delta P or pressure difference such that the flow is moving in the forward direction. Okay. Again, this requires some concepts from fluid mechanics, but I will just show you some equations. So when you read that subject, when you talk about flow in a pipe, okay. So this is your axial momentum conservation. So we'll talk about momentum conservation in radial and axial directions. So when you say axial, this is the term. You see dB by dx. So this has to be there for flow to happen for a normal pipe flow. Okay, and this is there's a long derivation. I will not do that for this course, but this is called Hagen-Poiseuille equation. This is basically name of the scientist, and this is referring to flow in a pipe. Okay, there's nothing more complicated. You have to like take a flow in a pipe. You have to consider what are the forces involved. But there's a little bit of derivation which requires concepts of fluid mechanics. But at the end of the derivation, you have delta P. So this delta P is the pressure difference between upstream and downstream locations. So that has to be there. That is how flow is established. Okay, so I'm just telling you as a matter of fact, but when you study this subject, you will be reading in detail how it is there and how it works. Okay, now coming to Bernoulli's equation. Okay, so now we have seen that pressure is there and that has to be maintained to establish flow, but that is not fitting well with Bernoulli, right? So as per, if you look strictly speaking, look at Bernoulli equation, you will say that P1 and P2 should be same. Okay, because the area is not changing, velocity is same, so the pressure also should be same. That is what Bernoulli will say. But the question that you should be asking is whether Bernoulli equation is valid here or not. Okay, so there is a very major assumption. Bernoulli has 4-5 assumptions that these are the conditions where Bernoulli equation is applicable or valid. Okay, So one of them is inviscid flow. Bernoulli assumes that the flow is inviscid or viscosity is zero. That is not the case here. Okay, here viscosity is playing an important part. That's why Bernoulli equation is not valid or not applicable. Okay, so again this will be covered in fluid mechanics. I will not go in more detail because you need lot of concepts. You have to like have some basic understanding, then you can be then you will be able to appreciate this idea. But the point here is that Bernoulli here is not applicable because of viscosity effects. Okay, is this clear? I will go to maybe chat box. If any questions, you can post it here. I hope I am just trying to give a little bit of idea. If it is clear, let me know. If you have more questions, please ask. So who asked this question? Are you clear now?
Yes, sir.
Fine.
Sir, in short, the pressure difference is for balancing the viscosity effect, right?
So viscosity, because of viscosity, there is a shear force. Okay, let me
Yeah.
go back to that slide. So shear force, there is a net force in backward direction. So pressure difference will overcome that. Okay, something is pushing you back, so you need to move forward. So that is what pressure difference is doing. But why this profile is parabolic, why this shear force coming to, that all will be covered in fluid mechanics. I cannot go in more detail in this subject without you having that background. That is the problem I have. Okay, so in simple terms, I've tried to explain. I hope you're clear with this. Fine. So the person who asked, is he clear? Should I go to the next topic?
Yes, sir.
Fine.
Yes, sir.
Let us go to see the thing is there is that like Bernoulli there are several other assumptions. Okay, thermodynamics we have lot of assumptions, so you should be very clear which equation or what condition is applicable at what scenario. Okay, so for example, ideal gas. Generally, we assume that air is an ideal gas, but we will look at some situations where this is not a good idea. It is not a good approximation. Air deviates from ideal gas behavior. Okay, so whenever you take some assumption, you should be clear with what are the errors involved and where this assumption is right. So, for example, from now on, all the processes which we encounter, we will blindly assume that this is quasi-static, but that may or may not be true in various scenarios. So we should know that if it is not quasi-static, what is the error involved? Okay. Actually, no real process is quasi-static. Quasi-static means that it has to be infinitely slow. No real process goes at that speed. Every real process has some finite speed. So it is an approximation, and you should be just clear what it involves and where it is valid and where it is really bad. Okay. Let us move on to next topic. So this we have done. Let us now talk about the pressure transducer. So again, some students asked for more detail, but I will repeat that this is not in your course. So basically, in this course, we'll talk a lot about pressure and temperature, but the idea is that you should just know what are the devices which are used to measure them. Okay. For if you want to know more detail about these devices, there is another course which is called mechanical measurements. So there, in that course, you will study. But what are the for the some instruments which I have mentioned? I will try to give a brief overview. Okay, so let us look at the pressure transducer, how it works. So this is a schematic. Okay, I am also giving this site as references. I have taken images from there. And if you want more detail, if you want to read in more detail how it works, then you can refer to those sites. Okay, so everywhere where I am taking some images or equation, I am citing the source from where we have got. So this is like ethical way of citing any reference. Okay, so let us come back to pressure transducer. So this is how it looks schematically, as you have seen the last slide. Okay, so this will actually go inside your pressure chamber. So if I have a box, I will screw this inside that box and pressure will be felt from this hole. Okay. So pressure is coming from this hole, and here I will have some electrical wire which will be connected to a computer or data acquisition system, that from there I can read how much pressure reading is there. Now the question is how it works. So basically what happens is, inside this, if you take a cut section, you'll see that there is a diaphragm here. Okay, it will be made of some flexible material that like rubber. So what will happen is, when we have some high pressure here, it will bend it. Okay, imagine that rubber is there in path of high pressure, so it will be bent little bit. Okay, let me draw it for you. So the diaphragm, which is flexible, which is made of flexible material, if you apply more force or pressure, it will bend a little bit like this, right? Now this diaphragm is actually equipped with strain gauges. So this is called a strain gauge. Okay, it is pasted on the diaphragm. So what will happen is that this strain gauge will measure how much it has deflected. Based on that, it will give you a signal that what is the pressure reading inside. Okay, so let us quickly look how this strain gauge work. So basically, this is like a small chip sort of thing, and there is electrical material. This is an electrically conducting material. Okay, it is like a metal wire or something, some specific alloy. Now, what happens is your electrical resistance, it depends on the length of this, diameter of this wire. Okay, so if you stretch it, what will happen is the wire will become long, and this diameter will decrease. So that will change your resistance. So that if you change resistance, that will be measurable by applying voltage. So you get different current for the same voltage. Similarly, if you compress it, you will also change the resistance and you will get a different voltage here. So based on that, your equipment will be calibrated, and based on how much change in reading we have, we can calibrate and give pressure reading. We can tell how much pressure has changed. Okay, is this clear to everyone? How this pressure gauge works?
Yes, sir.
Yes, sir.
Let us now talk a bit about thermocouple. Okay, so we have mentioned that there are two wire types, type A and type B. So these are just simple plain wires, but different metals or different alloys are used. Okay, so let us quickly go in a little bit of more detail. So what is the physical mechanism behind this? What is the effect that is going on? That is a thermoelectric effect, which is also called Seebeck effect. Okay. So what happens in Seebeck effect is basically we maintain two junctions, hot and cold. Cold will be maintained at room temperature, and this is subjected to high temperature. Okay. Now, because of some physical property that again I will not go in much detail. So what happens is there is different energy levels in different metals. Okay, which create a potential difference between the junctions. So because of some physical properties, we see that if you maintain these two junctions at different temperature, basically you need to maintain a temperature gradient. Okay, now what is a gradient? So you have some temperature here, let us say 100 degrees Celsius, and you have some low temperature here, let's say 0 degree or room temperature. So the temperature inside the wire, it is varying continuously from here to here. Okay, so at any point of wire you will see some dt by dx, where dx is along the length. So dt by dx is actually called temperature gradient, how your temperature varies with respect to length of the wire. Okay, so because of this temperature gradient, some electrical potential is created. Okay, potential difference, EMF, which can be measured. It is generally small, in millivolts you'll get the reading. And if you want more details, you can refer to this site. You will get a lot of information on Wikipedia or this website. Okay, any questions on this Seebeck effect? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, let us look at some examples. So as I said that these wires are of different types. Basically, they are made of different metals. Okay. So these are the general common type of alloys which we use. So thermocouple will be based on nickel alloy or platinum rhodium alloy or tungsten rhenium alloy. So these metals have different electrical properties, and then we join them as metal A and metal B. They work as a thermocouple. Okay, so let us look at some examples. So if you have nickel alloy thermocouples, so these are the different types. So thermocouples are basically denoted by alphabets. So type E, type J, A, B, C, D, like that. Okay. So each type is having different composition. So these are metal alloys. Okay. So chromel is an alloy, constant tan is an alloy. Similarly, we have different metal compositions. Okay. So there is no, I'm not going to detail, but you can have a look. If you're interested, you can read more about that. Now, what happens is that these different types have different temperature ranges. Okay, depending on what metal we have used, what is the melting point of that material, what is the working range of that material. So based on that, we get different temperature ranges. And there are two categories, one is continuous and short term. So if you want to measure quickly, you can have high range. If you want to use it for a long time, then you can use for shorter range. That's it. But basically, different for different applications, you use different type of thermocouples. So, for example, I was working on combustion. So we used to measure exhaust gases. So what is the temperature of exhaust gases? Then I've used K type of thermocouple. Okay. Now recently I am actually planning some experiments where I have higher temperature. So I'm buying B type of thermocouple. So in the next few months it will be here. So if anyone is interested, you can have a look at my lab. I can show you how B type thermocouple looks and how it works. And this is how we measure temperature. So basically, each thermocouple will give different voltage readings. Okay, for example, if you take K type, so K type will give you 40 millivolts if you subject it to 1000 degrees Celsius. Okay, so if your temperature delta T is at 1000, you will get 40 millivolt. That is how it is calibrated. So you measure how much millivolt you are given, you know which type of thermocouple you are using. So you can easily say what is the temperature that you have. Okay, so this is the working principle of thermocouple. Is this clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so this is how one K-type thermocouple looks. So we have, this is your hot junction, this is your cold junction, which is at reference temperature, and these are the different alloys, chromel and alumel. So chromel is made of nickel and chromium, alumel is made of nickel, aluminum, and other materials. Okay, so this again I will repeat that this is beyond your syllabus. I will not ask what alloy is made of what material, but just some people are interested. I am just sharing you some additional information. So at the end we put copper wire so that both the sides are same and there is no voltage difference because of this. So the only voltage difference is because of these two, chromel and alumel, and this is simply used to connect and measure the voltage. So this is the schematic of K-type thermocouple. Now different type, B type, A type, you will have different material. That's all. But the basic configuration will be same for all type of thermocouples. Whether you take B type, K type, C type, same configuration will be used. Okay. So actually, I am as I told, I am buying this B type. So you can see how they are specifying. So this works till 1800 degrees Celsius. What is the size, length? And then I also getting one reading. So this will supply voltage. So one temperature indicator will be used that will give you a reading in degrees Celsius or Kelvin, whatever you want. Okay, so last month I got the quote. Maybe by 1 or 2 months I'll buy. So if you want, you can have a look at. This is B type of thermocouple. So this contains platinum and platinum rhodium alloy. 30% I think is this. Okay. So with that we end this supplementary notes. And if you really are interested in measurement methods, then you should read this book. This is a good reference book for this type of measuring instruments like thermocouple, strain gauge, or pressure tube. So experimental method for engineers you should refer to. Then for this Bernoulli and all, you can refer to this book, but this will again be covered in your next semester. And you can get a lot of information from Wikipedia. Okay. So with that, I stop this topic and we'll move on to work and heat. Okay, let me stop the recording for this.